Swayam Prabha. Digital India. Educated India.
In the last two lectures, we have been talking about forecasting and various methods of forecasting. As you all know, the forecast of demand is a very important input to the planning exercise. And in today's lecture, we are going to be talking about utilizing demand forecasting for purposes of aggregate production planning. Aggregate production planning is the exercise of developing a overall plan for a company which specifies how resources of the company are going to be committed over the next 6 months to 1 year. So the typical planning horizon that we are talking about is a planning horizon up to about 1 year. And in this particular lecture, we are going to be talking about some of the basic concepts of aggregate production planning, and we'll see how aggregate production planning is actually useful for a company. This is the basic definition of aggregate production planning. So if you see, aggregate production planning is basically concerned with planning overall production. The emphasis is on overall production of all products combined, and this overall production could be in tons of steel, liters of paint, etc. And we are talking about a planning horizon generally next 3 to 6 months or even extending up to a year for a given forecast demand schedule. So the basic idea here is that the demand for the various products of a firm could be fluctuating, and if the demands are fluctuating, how do we commit our resources to meet this fluctuation in the demand? That is the basic intention. I think a word about why we call it aggregate production planning, and how is aggregate production planning different from production planning within the context of a factory. You see, for a planning horizon for the next 6 months or 1 year, the company is basically interested in knowing how the overall performance of the company shall be as the demand keeps on fluctuating. So a company might be manufacturing, let's say, hundreds of products. The demand for one product may be going up, the demand for the other product might be coming down, and as far as the hundreds of products are concerned, each demand would exhibit its own kind of behavior. So if the company tried to track the performance of these individual products, it could probably go mad in tracking the demands of the hundreds of products which are there. And since the company is interested only in the overall growth and the overall commitment of resources for the next 1 year, therefore it is interested in aggregating the demands of the individual products and talking about the aggregate production plan rather than talking about individual production plans. So, if you are talking about a steel plant, for instance, a steel plant could be manufacturing sheets, scalp, various types of ingots of different sizes, rail sections, strips in a variety of sections. So, you would have a large variety. But when the managing director of the steel plant wants to know how the steel plant would be performing over the next year, he would probably be concerned about the total production in terms of tons of steel of all types of products put together. So, tons of steel would be a convenient aggregate measure of the performance of the company, and you could then aggregate the demand of all the products in terms of the total tons of steel and use this as an aggregate measure of the requirements of the company. Similarly, if you are talking about a paint manufacturing company, a paint manufacturing company produces paints in different colors, different sizes, and for different applications, and for each of those paints the demand would be different. But if you want an overall idea of how the paint manufacturing company is performing, you could probably aggregate the total requirement of paints and say what is the total liters of paint requirement for the whole company as a whole. This concept could be extended to even an automobile manufacturer, for instance. If you talk about an automobile manufacturer, let us take the typical example of Maruti Udyog, for instance. The company produces different types of cars. It produces a Maruti 800, it produces a Zen, it produces a van, it produces a Gypsy, it produces a Versa, and so on. It produces different types of cars, and the demand of these cars will be different over the planning horizon of the next 1 year. But if the company is trying to find out what would be its growth level for the next 1 year, it could probably try to mix up the demand of all these cars. Now, how would it mix up the demand? It could probably have to think in terms of a unit like standard passenger units, standard passenger cars. So, maybe they might say that a Maruti 800 is like 0.8 of a standard car, a Maruti Zen is like 1 standard car, an Esteem is like 1.2 standard passenger units, and develop some units like this, and then ultimately measure the performance of the company in terms of standard car units, something like this, and then it would have an aggregated variable which would be able to deal with this. So, the point that we are trying to say is, apart from this aspect of focusing on the overall growth, the second major advantage of using aggregating the demand is that normally if you have 50 products and you make their forecasts and then you try to work with individual forecasts, each forecast will be subject to some errors, and if you try to combine these forecasts, the aggregate demand figure would be subject to much less error, because the positive and negative errors will tend to randomly cross each other out, and therefore there is greater accuracy in obtaining the aggregate demand forecast than the individual demand forecast. So, this is another reason for dealing with aggregate production planning. So, the whole process in aggregate production planning is essentially to determine the aggregate forecast first. So, you do a process of aggregation, do aggregate production planning. Once you have done it, you will have to disaggregate it to obtain the individual pattern of demands, or rather production levels for individual products in that sense. So, I think this perception of aggregate production planning must be kept in mind. Basically, what are we trying to do in aggregate production planning? Basically, what we are trying to say is, we are working with the forecast of demand, and we are trying to work out the capacities, cost, and commitments that you are making. So, you know that this is the capacity of my plant, so much in January, so much in February, so much in March, because you might have committed capacity to other products. So, the capacity availability in different periods is known. So, you know the various types of costs that are incurred, and you are therefore trying to find out how these capacities should be committed to the aggregate demand over a certain period of time, and this is what we call an aggregate production plan. From the aggregate production plan, we are then able to work out the workforce requirement over the planning period, and we are also able to determine the machine time allocation over the planning horizon. So, basically this is the purpose of aggregate production planning, in trying to determine the commitments of the capacity to the various products. We have already indicated that the basic problem in aggregate production planning that we are trying to solve is the problem of meeting a fluctuating demand. If you were sure, for instance, that the demand in each month is going to be 100 units and this will continue ad infinitum, then production planning will be a relatively simple affair. But that is not what happens in practice. In practice, demands keep on fluctuating. You have to forecast these demands, and therefore let us be clear about the options that management has to meet fluctuating demand in any business. How can it meet a fluctuating demand? Probably the first method, and one that is used quite commonly in industry, is to build inventories in slack periods in anticipation of higher demands later in the planning horizon. So, you can keep on building inventories when there are no sales, in the hope that some future you will be able to sell off the inventories that you have made. This could be a good strategy provided the demands actually show up in the future. But if you have been able to, if not been able to forecast the demands properly, then this could be a risky strategy. You probably are aware that in the Maruti factory in Gurgaon, at one stage they had such a large stock of cars that they had to procure additional land to just store these finished cars outside, and so much so that the cars were actually getting damaged in the adverse weather conditions in which they were being stored. So, this strategy of using inventories in slack periods in anticipation of higher demands may work in practice, but it is not without its problems. The other option could be that you could carry back orders or tolerate lost sales during peak periods. Do you know the difference between a back order and lost sales? A back order is something when the customer comes to a shop and you don't have the item in stock, and he places an order with you and he is willing to wait. So, whenever you are able to supply, you give him the order. So, that is called back ordering. A lost sale would be that a customer comes to your shop and he finds that you don't have the brand of shampoo that you need, and therefore he just walks away to some other shop, and that is a lost sale. So, both lost sales and back orders are actually situations which occur when there is a shortage, when you don't have enough stock available of whatever item is demanded. So, whenever the stock level is positive, you build inventories. Whenever the stock level is negative, you either carry back orders or tolerate lost sales, in that sense. The third option that management may have to meet a fluctuating demand is to use overtime in peak periods, undertime in slack periods to vary output while holding workforce and facilities constant. This is a very common strategy, isn't it? This is the kind of strategy that students typically tend to use. When there is a peak period, that is 5 assignments are to be submitted, they work overtime at night and get these assignments ready, and otherwise when there is a slack period, they they use under time in slack periods, they do not work, and that is the way they vary their output, and while holding the workforce and facilities constant. I think another point that needs to be mentioned in the context of aggregate production planning is that normally we are not talking about the option of increasing machinery and other kind of infrastructure within your plant. For instance, if there is a need, if there is an increased demand for something, one option might be to set up another factory. Now, we are not talking about those capital intensive options in this particular situation, because our planning horizon is typically 1 year ahead. So, we are talking about those options in which generally the facilities are constant, though of course workforce can be varied in general. The other option available to the manager for dealing with fluctuating demand is you can vary the capacity by changing the size of the workforce through hiring and firing. It is a very common strategy these days, right. You probably heard or read a couple of days ago about Cadbury's laying off something like 20,000 workers all over the world, right, in their various plants. So, they are adopting this strategy of changing the size of the workforce through either hiring or firing. So, most of the companies fire their workforce, and when there is a need you can always hire the workforce. Okay. So, changing the capacity by hiring and firing is a very common strategy. It is actually a capacity that has, it is a kind of a
contract labor.
That is right, it could be contract labor. For instance, most farmers would engage additional labor when they require them for purposes of reaping the harvest, and then when they do not need them they would fire them, right. This kind of thing is so it is exactly that. But hiring and firing as a typical term, as a normal in normal parlance, is the legacy of the American culture. The American culture, people are very fond of hiring and firing, right. You find that an executive is doing very well, he is given a promotion today, but when he comes to work next Monday, he finds that there is a pink envelope on his desk which says, "Thank you Mr. Ralph, you are fired today because we do not need you, and here is your check for whatever number of days you have served us." This kind of culture prevails more in the United States, not in India as much, though of course the with the advent of the multinationals and so on, this kind of culture is also coming into being, the hire and fire culture. But normally when you talk about employment in the typical government of India, there if you are hired once, you are fired only when you retire, isn't it, that kind of a situation. But then this is an option available to management for changing capacity by changing the size of the workforce through hiring and firing. I would like to mention here that hiring and firing is not without its costs. When you hire people, you have costs of hiring, that is the process of selecting people, conducting an interview, training people before they actually become productive. So, these costs are the costs of hiring, and similarly when you fire people, there is a cost associated with firing as well. There is loss of customer goodwill, and the loss of customer goodwill would mean that the person whom you have fired will probably spread the message in other organizations, don't ever join this company, because they hardly keep you for 2 weeks and then fire you or something like that. So, that reputation travels. So, there are costs associated with hiring and firing, and one of the major purposes in aggregate production planning is actually considering these various costs which are associated with these various options, and try to select a strategy which is the optimum strategy in terms of meeting the fluctuating demand. You can vary the capacity through changes in plant and equipment, but generally, as I said, this is the long term option and is not considered when you are talking about aggregate production planning. Okay. So, the point really is that each option that we have considered here involves cost. The cost may be tangible or intangible cost, and the aim in aggregate production planning is to choose the best option considering the various costs. So, it is essentially an optimization problem with these types of costs, fluctuating costs, and the kinds of constraints that we have just tried to mention. So, before we talk about the problem involved, let us try to identify the kinds of costs which are there in typical aggregate production planning. One of the major costs involved is procurement cost, right. So, whenever you are producing, you have a typical option of either buying the material or producing the material. In either cases, procurement is to be made, right. You can either buy the material for 100 rupees and then process it within your factory, or you can procure the item maybe for 500 rupees, whatever it is. So, costs of procurement have to be taken into consideration, and the costs of procurement, in fact, all these costs could be fluctuating or varying with the time period over the planning horizon. Then you have costs of production. Cost of producing a piece in the first period might be 100 rupees, in the next period it might be 110 rupees, and then it might be constant at 110 rupees a piece, and then it might go up again in the sixth period to something else. Inventory holding costs. The inventory holding cost is that cost by which, if you produce something in a certain period, whatever is not consumed will have to be held for that particular period, and that is the inventory. So, there are costs of storage, costs of spoilage, cost of pilfering, etc. These are basically all aspects of inventory holding costs. And typically, one of the most common components of inventory holding costs is the loss of interest on the capital that you have invested. For instance, if I stock something worth 1000 rupees, if I had kept that 1000 rupees in the bank or given it to somebody else, I would have been able to earn some interest on it. But by holding it in inventory in the form of a car or a whatever product I have actually foregone any returns on that particular product. So, this is actually what we mean by saying that there are always inventory holding costs. Shortage losses associated with back orders and lost sales. So, depending upon the situation, that is, if you are not able to supply an order because you do not have the quantity ready with you, then you incur a shortage, and the shortage losses could be in the nature of back orders. So, in a back order, the cost would be in terms of rupees per unit time, right, because you are satisfying the demand at a later point of time. But for a lost sale, it is a one time loss. So, it will be like so many rupees per units lost. The element of time would not be there in lost sales. So, that would be the unit of a back ordering cost and a lost sales. Then we talk about costs of increasing and decreasing the workforce. These are typically the hiring and firing costs that we were talking about. If you increase the workforce, the cost of employing additional people, training them, and bringing them up to the mark so that they can contribute effectively to your process, that is the cost of increasing the workforce. Cost of decreasing the workforce could be the cost of idle capacity, or it could also be the cost of loss of goodwill. So, these types of costs are involved. Then we have the cost of overtime and undertime. cost of changing production rates. What can happen is that there could be setups, there could be opportunity losses, etc., and these are the costs of changing the production rate. For instance, if you are producing at a certain level in the month of January and you decide to change the production rate in February, it would either mean that you have to change some setups, make some new adjustments in your plant, and that's the kind of setup cost that you have here, and or there could be some kind of opportunity losses as a consequence of these kinds of decisions. Let us now take a simple example to show how aggregate production planning could be done. Suppose that we have data on demand for the next, let's say, 1 year. So during the first period the expected demand is 100, and I also have a cumulative demand figure which tells me what is the cumulative demand up to the end of that period. So in the second period the demand is 180, the cumulative demand is now 280, and so on. In the third period the demand is 220, so this added to 280 will give me 500. Now the significance of this cumulative demand is that it tells us that up to the end of the third period the total demand for all the periods is 500 units. Similarly, the total demand up to the end of the 8th period is 1500 units, and this is how the demand has been fluctuating over the various periods, right. So this information would be available to us from a demand forecast. We have been talking about demand forecasting in the previous 2 lectures. So basically the output of an exercise of this kind would be that we would have access to information like what is the expected demand over the next period. What we are saying here is that these are 4-week periods, so there will be 13 4-week periods in a year, 52 weeks. So we have the demand figures available for all the 13 4-week periods. So these are like 4-week periods in that sense, and the cumulative demand is 2600 for all these 13 4-week periods, that means for the entire year. Now what we would like to do is to find out that in the face of this uncertain demand, what would it be, what should be the right policy for the company to produce so that you can meet this kind of demand. And we will approach this problem from an intuitive perspective, and we will see how we can solve this particular question. We will use a graphical procedure, and incidentally this graphical procedure is the most common one with practical managers, because they find it simple and it does not involve any complicated mathematics, right. And obviously the price is in terms of the fact that this leads to only a heuristic solution, it does not guarantee an optimal solution, but it has certain advantages to offer. The first thing that you do in the procedure is that you plot the cumulative demand. So this solid line which you see here is a plot of the actual cumulative demand that we had in the table. So you plot the cumulative demand which is shown here, and you go up to the 13th period and you have this demand. Now let us consider 2 possibilities, we call them plan 1 and plan 2. After all, what we need is, what is a production plan? A production plan is nothing but a path going from this point to this particular point here, and any line which goes from here to here is actually a production plan. And since infinite number of lines can be drawn from 0 to this terminal point, therefore there are infinite number of production plans. But normally what is the ideal thing for a production manager? He would not like to vary the quantity that he produces every year. So, the total quantity that is to be produced in 13 periods is 2600. So, if we assume that a constant production level is to be maintained, 2600 divided by 13, we should maintain a constant production level of 200 per period, and we would have a constant level of production. If you plot this plan is actually shown by this top dotted line. It is a straight line from here to here, and that is what it is. Do you notice something about this plan 1, that is constant production? If you plan at a constant production rate, you compare the actual demand forecast with this line, you find that the actual demand forecast for most of the time except somewhere here is below this line. What does it show? It shows that the cumulative production is greater than the cumulative demand, which means if this particular line, that is the production line, is above the cumulative demand line, we would have costs of carrying inventories. So, one thing that you can immediately see from this plot is that if we follow this policy of having a constant production level of 200 per unit, in most periods we will be carrying inventories, except in some periods there could be a shortage. This amount could be calculated, as we will do subsequently. So, if the cost of carrying inventory is not too high, this should be a good plan, because you are most of the time you are not incurring any back orders or shortages, and you are carrying inventories, and this is what it is. Of course, one might say that another possible plan may be that you follow this demand line closely, which means you produce exactly as per demand. That could be a production policy. So, if you produce exactly as per plan, what will happen? That your cumulative production will exactly follow this, and you will neither be carrying inventories nor will there be a shortage, but the kinds of costs that you will involve are cost of changing production rates every period. So, there would be a situation where you would not have to carry any inventories, you would not have to incur any shortages, but you will have to change production every period, because you are following the demand, you are chasing the demand. It is actually a chase model, and when you are chasing the demand, every time you are changing the period, there is a cost involved. This cost could be through either hiring and firing, or it could be by varying production rates, or whatever it is, in various ways. So, you would have a situation like this. So, this policy, although good in terms of minimizing the costs of carrying and back orders, it would not be so good from the point of view of changing the production rates, because you will have the cost of changing production rates will be pretty high. Practically, you will be changing the production rate every month, and this would mean havoc for the production manager. He would not like to do this kind of thing. So, you might argue that can we not have a intermediate plan? Now, the intermediate plan could be that rather than changing this production rate every period, we have minimum number of changes, and then see, for instance, by looking at this curve, you might find, for instance, that it is going up and there here. You could have a policy that, let us say, up to the 5th month I maintain a constant production rate. So, in these months I am having inventories, and in this period I am carrying shortages here. So, the total production here, the cumulative demand up to this level is 750. So, 750 divided by 5 is 150. So, the policy is that you carry on the varying production level at a rate of 150 per period during the periods from 1 to 5. So, you get this lower dotted line up to here. Then you can look at this and say maybe up to here, from this point to the from the 5th period to the 11th period, you again calculate what the cumulative demand here is, and then see divide this by the total number of periods, and you get 250 per period is what you produce during the period from 6 to 11. So, your production plan is something like this, and in the subsequent periods 12 and 13, which are the last periods, you again know that this is what you have to produce. So, you are producing 175 per period during the period from 12 to 13. So, what have we got? What is the advantage? The advantage is that this is like a compromise plan. It shows that there will be some holding inventory, some shortages, but the number of changes in production are limited, because during the entire planning horizon, first 5 periods we are keeping the production level at 150, then we are changing it to 250 during this period, and then we are changing it to 175. So, one slope, next slope, next slope, only these 3 slopes are involved, and it involves starting with this production period, then only 2 changes, one change here, another change here, as compared to the earlier plan that we were talking about, where you are changing the production level each time. That would be much more costly, right. So, the basic advantage of the graphical procedure is that it helps us to, in fact, by looking at the demand profile, suggest what could be the possible alternative plans, and this is the feature that practical managers love most. What they do is they can put down their plan on it, and then basically it can be evaluated. So, if you put down a couple of plans on this particular line, you can then evaluate them and pick up the best one. Evaluation is generally done in a convenient tabular form like this. We are talking about plan 1, which is constant production. So, production is constant in all the periods, and because of the varying we have the demand. So, if you produce 100, the demand was 100. So, the inventory at the end of this period is going to be 100, right, and the back order is 0, and the capacity change is plus 20. Assuming that the capacity was set for something else, the capacity changes so much, the overtime is 0 and the subcontracting is also 0, and you compile this table. Obviously, what you notice from the plan, the first plan, is that there are no back order costs generally. There is only one capacity change cost. There is no overtime cost, no subcontracting cost, at least in the first 8 months, but there are mostly costs of holding inventories. So, depending upon the relative cost of this, you can determine what the total cost is, right. You can
What is meant by capacity change?
capacity change means that if I am operating at 100 units today, and if I change this capacity to 120 in the next period, there is going to be some cost associated with that capacity change. That is what it is. So, this plan, for instance, it does incur some back order costs, as I said, in the 10th, 11th and 12th periods. So, what you have to basically do is, you know these various cost parameters. You have to talk about the cost of production, the cost of inventory, the cost of back order, the cost of capacity change, the cost of overtime, the cost of subcontracting, and we now know each of these. Multiply these with the appropriate figures and you will get a rupee figure here. So, you will know what is the total rupee value in terms of the various types of costs involved for this particular plan. We can do an exactly similar exercise for the second plan. What was the second plan? We were keeping the production constant up to the 5th period, up to 150, then it was 250, and thereafter it was 175 in the last 2 periods, right. So, we had, so you can calculate similarly the inventory, the back orders, the capacity changes, the overtimes and the subcontracting which is necessary. Of course, this is all based on a certain set of assumptions. We will talk about them in a short while, and ultimately even for this plan you will have this. So, the inventory costs here are 0, back order is there, some capacity change, that means reduction in capacity, overtime costs, subcontracting, all these costs are there. So, if you know the relative values of these particular costs, you can find out this particular component. This is the basic framework that you can follow for analyzing a plan. So, you can compare plan 1 with plan 2 with plan 3, find out the overall costs, and then take a plan which is the best for your use. So, this is how the graphical method will actually be a way of choosing the best plan out of the ones that you have been trying to, that you have listed. So, if you have not listed the optimal plan, obviously you will not get the optimal plan, right. So, it is a heuristic procedure, but it is good in the sense that it tries to consider all the costs involved. Now, in the carrying out those computations, some assumptions were made which are quite commonly followed. All shortages were assumed to be backlogged, which means that we did not have any lost sales. If there was a shortage of 20, we said that it is backlogged. Regular time capacity was taken to be 200 units per period. The maximum overtime capacity was taken to be 20% of the regular capacity. So, 20% would mean that the maximum overtime was 40 units per period. Overtime is generally preferable to subcontracting. That was an assumption. See, normally you would tend to produce something on regular time, followed by something on overtime, and if you cannot make it on overtime, then you will subcontract. That is the idea. So, the relative preference was regular time, overtime, and subcontracting. Assumed initial inventory was 0. The initial regular time production capacity was 180. So, these were the figures that were assumed, that last year the company was operating at an initial capacity of 180. So, that this year if you want to produce 200, you have to change the production capacity to 200. So, the production capacity change costs are plus 20, and that is what you found in the table. So, you will always have a set of situations something like this, and you can use the graphical procedure, which is the simplest method of aggregate production planning, to actually identify the best plan of action for your situation. However, the biggest limitation with the graphical procedure is that it does not give us an optimal solution. It does not give us the solution which has the minimum cost, and therefore, we have procedures which in fact are dependent to a very large extent on the nature of costs, and depending upon the nature of costs, we can choose an appropriate solution procedure. For instance, if you have a situation like this, where the production cost in a particular period, say xt is the production in period t and ct xt is the production cost, if this is linear, that means it passes through the origin. It is like saying that the slope of this line is the cost per piece, right. So, if it is whatever is the cost like this, it is a linear production cost. Similarly, the inventory cost could be of two kinds. It could be a situation where the inventory is positive, which is the holding cost. A situation when the inventory is negative, which is the shortage cost. Because what is positive inventory? You are holding stocks. What is negative inventory? You have items on back order. So, it will be one of the two situations. Either I can supply immediately 20 cars if I have more stocked with me. So, it is a situation where the inventory level is high, and if there is any demand less than this, I can supply it offhand. But in this case, there is a shortage. So, I back order. Right? If somebody places an order for 20 cars and I do not have 20 cars in stock, I will say okay, the next 2 months I will manufacture these 20 cars and supply them to you. That is back ordering cost. But back order is also at a cost, right? It is in terms of loss of goodwill, whatever it is. So, there are these costs which are determined by the slopes.
So, suppose Maruti has allocated some land for storing manufactured cars. So, if the inventory is 0 or if inventory is 100, then what difference does it make, sir? Because even if it is zero, the land is lying unused, and even if we store 100 cars, so there won't be any extra cost on that.
You can look at it this way, that if it has allocated some additional land, if it is not stocking something and some cars on it, he can probably give it on rent and earn revenue on that particular land, which it is forfeiting by putting some cars on stock. So in that sense, it's a potential loss of an opportunity, which is a cost. That's what it is, right? So it would always be a situation of this nature. So if you have linear costs of this kind, that is, production costs are linear and the inventory costs are also linear, then you can use linear programming for solving this problem. You can use a simplified transportation model, or you can use a transportation model for solving this particular problem. I am just trying to give you an overview of the various solution procedures. In the next lecture, we shall go into the details of how these models can be applied for determining the optimal solution, right? But the point here is that these solution procedures that we have identified here are valid only if the cost structure is linear for both production costs and for inventory holding and shortage costs. Then you can use any of these procedures. On the other hand, if costs are convex, this is now a case when all the costs are convex. What do you mean by convex costs? That is, the production cost is something like this. What does it mean? That if you produce the first unit, the cost is less. As you keep on producing more units, the cost keeps on increasing, right? When do you think this would be a relevant thing to happen? This would happen, for instance, when initially you have lower costs, and subsequently beyond a certain production level, the costs are higher. So if you are talking about regular time production, overtime production, and subcontracting, the cost slopes would be progressively increasing, piecewise linear in that sense, right? So those costs are therefore convex. In a convex cost, if you join any 2 points on this cost function, the line segment lies wholly above this particular cost, right? That is how you define a convex cost function. Similarly, you will find that the inventory costs are also convex. This is convex, this is convex. In a situation like this, where the costs of production, costs of inventory are convex, again you can use a transportation model, but after piecewise linearization. Piecewise linearization is quite common: regular time, overtime, subcontracting. The cost will increase per unit. Or another very classic example of convex costs is a model due to Holt, Modigliani, Muth and Simon, 4 people, and they have developed what are known as linear decision rules, or LDRs, and they are typically valid for convex costs of this kind. And in fact, what they have assumed is that this is based on a case study in the paint manufacturing company, and for that paint manufacturing company, they have approximated all costs as quadratic costs of this type. This is a quadratic function, and when you differentiate a quadratic function, you get linear functions. So the solution that you get is a linear decision rule. That is how the term comes about. We'll have a quick glance at this particular method. If the costs are concave and piecewise concave, this is the most complicated category of costs mathematically. You are saying that the cost is first increasing and then flattening out. So what happens is, this is like economies of scale. The more you produce, the lesser is the cost per unit, right? Similarly, for inventory costs, you have this behavior. And for concave and piecewise concave costs, we can use dynamic programming for determining a solution, or we can use a network flow solution which is based on the shortest path in a network developed by Wagner and Witten. In fact, it's Wagner and Witten, so it should be Wagner and Witten, right? Now, just to give you an idea of these linear decision rules, let's quickly run through this example. This was a study done by Holt, Modigliani, Muth and Simon in 1955 on a large paint manufacturing unit, and what they did was they defined these variables. Wt is the workforce level in period T, T going from 1 to capital T. Xt is the aggregate production level in period T, and then we have It is the actual production net inventory at the end of period T, and It star is the ideal aggregate net inventory at the end of period T. Okay. So what is done in this particular model is that various types of costs are modeled. How they are modeled? Say regular time payroll cost. What is the regular time payroll cost? It will have a fixed component and a variable component like this. So this is the workforce, Wt, number of workers in period T. So this cost is modeled by C1 Wt plus C13, which is a constant. So C1, C13 are constants. Similarly, workforce change cost. Workforce change cost is something like this. This is for shortage and this is for holding inventory. So you have Wt minus 1 is the increase or decrease in workforce. So this is the hiring cost, this is the firing cost. They approximate this function by this quadratic component, and this quadratic component is written as C2 Wt minus Wt1 minus C11 whole square. So this is how they model the workforce change cost, convex costs. Then the overtime cost. Overtime cost will also be that beyond this level the cost goes up. So this is approximated by this particular function, and it is xt minus C4 Wt whole square multiplied with C3 plus C5 xt minus C6 x into Wt plus C12 into xt Wt. You see, it is nothing but a function of all xt and Wt. So the xt minus Wt whole square, xt term, Wt term, and the product of the two terms. All the components are there with the various parameters. Now these parameters will have to be determined from the actual costs of the company. Similarly, inventory related costs, which are of this nature, are approximated by a function which is quadratic of this type, and then you have C1 It minus It star whole square, which is equal to C7 into It minus C8 minus C9 into dt, whereas dt is the demand for the tth period whole square. And these are all the costs. And then this was just to give you an idea that once you sum up all these costs and you take partial derivatives with respect to W1 star and X1 star, which are your variables, you will get linear functions of dt, W0, I0. So what really happens is that W1 star, Wx1 star are now coming out to be linear functions of dt, W0, I0 in the previous period. Similarly, W2, X2 will be linear functions of W1, X1, and so on. So those are the linear decision rules that this particular model is actually trying to use. There are a number of other methods to handle aggregate planning, aggregate production planning. These are some of the models which are available in the literature for solving aggregate production planning problems of this type. So a very common formulation is a linear programming formulation. So if the costs are linear, you can easily write down an LP to represent the costs and the various constraints. What would be the constraints? The constraints would simply be inventory balance equations. I have so much, I produce so much, I sell so much, and therefore at the end of the period I have so much. This kind of a constraint will have to be written for each period. That is the inventory balance equation, conservation of mass equations, right? So then any other constraints that you may have, and then the costs that we have discussed, that will constitute your objective function. So this is the typical LP model formulation. Search decision rules was one category of procedures which were actually determined by Taubert, in the sense that you talked about one type of rule, another type of rule that you are using, and you can then talk about a combination of these rules. It's like rule 1 into alpha plus rule 2 into 1 minus alpha, and you are trying to basically search with what particular value of alpha you would have a rule which would give you an appropriate kind of solution. These have not come out to be very popular in aggregate production planning. Goal programming formulation is an extension of linear programming, and it would be useful when you are dealing with multiple goals. Parametric production planning is a procedure developed by Jones, in which basically some parameters are introduced which can change over certain periods, and through the process of optimization you are actually determining the values of those parameters. That's the basic idea. And a management coefficients model is an approach in which you basically try to talk to different managers and find out what is the optimum strategy, and then you try to find out something like a weighted average of the methods that are suggested or the strategies that are suggested by different managers, right? Which might happen, for instance, we give you the example of the graphical procedure. We had two plans. So one could be possibility of product one, manager 1. It could be, second one could be the idea of manager 2. So what you can do is, if you thought of maybe 75% confidence in this manager and 25% confidence in the other manager, you could take the two plans and find out what would be the production quantity in individual period, something like that. So that would be the approach that you would follow to determine this. So there are a variety of methods for solving the aggregate production planning problem. To conclude, let us summarize what we have tried to see in this particular lecture. We have seen that aggregate production planning is relevant for fluctuating demands for medium term horizons, typically in the range of 6 months to 1 year. I think that is one key factor that you have to understand, that basically it's the horizon of 6 months to 1 year that we are trying to see, and we are talking about the fluctuating demand of the company, and we are trying to see how the resources should be allocated to meet that fluctuating demand. This is the problem. So this is the problem that we have been trying to see. A simple graphical procedure that generates good solutions by examining the demand pattern was presented. It was simple in the sense that you could pose a procedure and then just find out what is the cost of that procedure. That was the idea. And there could be various ways to meet a fluctuating demand. It could be through hiring, firing, through storing inventories, through shortages, through back orders, etc. So we saw that there were a variety of ways. In fact, the very fact that there are a variety of ways, that is why the optimization problem is so intense. You have to find out what is the best way. And finally, we have taken an example of solution procedures including the linear decision rules, where basically the costs were convex, and because they were modeled by a quadratic function, when you differentiated the cost function, you actually landed up with linear decision rules, and this was one approach. Now in the next lecture we shall be talking about some specific procedures that are used for optimizing the production plan, that is, finding out what is the best way to determine the production plan. Thank you.